If you're studying for the CCNA, OSPF is one of those topics that feels confusing until you get the big picture. OSPF stands for Open Shortest Path First, and it's a linked state routing protocol. In simple terms, it's a routing protocol used inside a company network, not for the public internet. Now, here's why OSPF matters. It's built for large networks, it converges fast, and it communicates using multicast. It's also an open standard, which means it isn't locked to one vendor. You'll see it everywhere. And the core brain behind OSPF is the shortest path first algorithm, also called Dijkstra's SPF, which it uses to pick the best route through the network. So, what does link state actually mean? Each router describes itself and its interfaces to its directly connected neighbors, and that information gets passed along unchanged from router to router. The result is the key idea. Every router learns the full picture of the network, every router, its interfaces, and what they connect to. That shared map is stored in something called the LSDB, the Link State Database. Think of the LSDB like a network blueprint. Once the router has that blueprint, it can run SPF and compute the best path to every destination. And here's the payoff. OSPF isn't just following directions from neighbors. It's making decisions based on the whole map. Now that you understand how OSPF thinks, let's talk about how it actually works. OSPF follows a very predictable process. Every time, no shortcuts. First, routers discover neighbors using hello packets. Then they decide which neighbors are allowed to become adjacent. Once adjacencies form, routers exchange routing information, build their link state database, and finally run shortest path first to calculate the best routes. Those routes are then installed into the routing table. And if the network changes, a link goes down, a router fails, OSPF repeats the process. That entire cycle happens automatically. Now, here's a distinction that trips people up on the CCNA. A neighbor is simply a router you've discovered using hello packets. That's it. An adjacency is something deeper. Adjacency means two routers have synchronized their databases and are actively exchanging routing information. So here's the rule you need to remember. Hello packets create neighbors. Adjacencies exchange routes. Not all neighbors become adjacent, and that's not a problem. In fact, OSPF is designed that way on purpose. We'll explain the why later, but for now, make sure that difference is clear. To understand OSPF, you also need to understand how routers communicate. OSPF doesn't just send routes. It uses 5 specific packet types, each with a very specific job. First, hello packets. These are used to discover and maintain neighbors. Next, database description packets, or DBDs. These don't carry the full database. They're summaries used to compare what routers already know. Then you have link state requests, or LSRs. If a router realizes it's missing information, it requests it. That missing information is sent using link state updates, or LSUs. And finally, link state acknowledgements, which confirm that LSAs were received. Each packet type exists for one reason: to build and maintain a consistent view of the entire network. The next distinction is subtle and very important. OSPF packet types are how information is sent. LSAs, or link state advertisements, are what is being sent. An LSA is the actual topology information: routers, links, and networks. These LSAs are stored in the link state database, and they're what the SPF algorithm uses to calculate routes. Here's the clean way to think about it. An LSU is the container. An LSA is the content inside. Or put another way, LSUs carry LSAs. If you mix those up on CCNA or in general, OSPF will feel way more confusing than it needs to be. Now that you understand the packet types and LSAs, we're ready to talk about the most important packet of all, hello packets, because everything in OSPF starts there. If OSPF had a heartbeat, hello packets would be it. Hello packets are the foundation of everything OSPF does. Before routes, before databases, before SPF, routers must exchange hellos. Hello packets are used to discover neighbors, maintain neighbor relationships, and detect failures. Routers send hello packets out every OSPF-enabled interface, at regular intervals, typically 10 seconds, as long as OSPF is running. If hellos stop arriving, OSPF assumes something is wrong, and that triggers routing changes. So, if neighbors don't exist, nothing else in OSPF works. This is why, when troubleshooting OSPF, hello packets are always the first thing you think about. And no, hello packets don't just say hi. They carry critical parameters that routers use to decide whether they're allowed to form an adjacency. Let's go through what's inside an actual hello packet. Each hello packet includes the router ID, the area ID, the hello timer, the dead timer, authentication settings, the stub area flag, and a neighbor list. Routers the sender already sees. The hello timer controls how often hellos are sent. The dead timer controls how long a router waits without hearing a hello before declaring a neighbor dead. And here's the rule you must remember. Hello timers and dead timers must match, or adjacency will never form. The stub area flag tells a neighbor whether the router believes it's in a stub area. If one router thinks the area is a stub and the other doesn't, adjacency fails, no exceptions. Here's your adjacency rule. It's very important. For two routers to become adjacent, they must agree on the area ID, hello timer, default 10 seconds, your dead timer, default 4 times the hello timer, authentication settings, stub area flag, and they must be on the same subnet. If any one of these doesn't match, routers may still see each other, but adjacency will never form. That's why you'll sometimes see neighbors stuck in INIT or two-way. Now that we understand hellos and adjacency requirements, the next piece is router ID, how OSPF uniquely identifies every router in the network. And this one shows up everywhere on the CCNA. Every OSPF router needs a unique identity, and that identity is called the router ID or RID. The router ID is a 32-bit value, often written in IPv4 format, that uniquely identifies a router inside the OSPF domain. OSPF uses the router ID everywhere, in hellos, in LSAs, and during elections, so stability matters. If you don't manually configure a RID, OSPF chooses one automatically, and it follows a strict order. First, OSPF looks for a manually configured router ID. If none exists, it looks for the highest IP address on a loopback interface. If no loopback exists, it uses the highest IP address on an active physical interface. This is why loopback interfaces are preferred. They don't go down. To manually configure a router ID, in global config, router OSPF 1, followed by router ID 1.1.1.1. And here's the critical CCNA rule. The router ID is chosen when the OSPF process starts. If you change it later, you must restart OSPF using the command clear IP OSPF process. This can be disruptive, and typically you would wait for a natural or scheduled restart of the router. OSPF uses wildcard masks, not subnet masks. A wildcard mask is the inverse of a subnet mask. Here's how to think about it. 0 means this bit must match. 1 to 255 means this bit can be anything. For example, if you have a subnet mask of 255.255.255.0, your wildcard mask would be 0.0.0.255. If you have a subnet mask 255.255.255.252, your wildcard mask is 0.0.0.3. In OSPF, wildcard masks are used in the network command to match interfaces, not to define routes. Remember that. As OSPF routers form adjacencies, they move through defined neighbor states. You don't need to memorize every packet exchange, but you do need to recognize what the states mean. Here are the key ones. Down, no hellos received. INIT, hello received, but no two-way communication. Two-way, bidirectional hellos confirmed. EXSTART and exchange, database negotiation and summaries, loading, missing information requested, and full, LSDBs synchronized. Here's a key CCNA rule. Two-way means neighbor, full means adjacency. And on Ethernet networks, two-way can be completely normal. OSPF behavior changes based on the network type. At the CCNA level, focus on two: broadcast networks like Ethernet LANs and point-to-point networks like serial or PPP links. Broadcast networks are multi-access. Multiple routers share the same network. Point-to-point networks connect exactly two routers. And the difference explains a lot of OSPF behavior. On multi-access networks, forming full adjacencies between every router doesn't scale. So OSPF introduces the designated router, or DR, and the backup designated router, or BDR. The DR acts as the central exchange point for routing information. The BDR is the standby. Routers that are neither are called DR other routers. DR and BDR elections happen per interface, not per router. The election rules are simple: highest OSPF priority, highest router ID as a tiebreaker. Your default priority is 1. Priority 0 means a router can never become a DR or a BDR. On Ethernet, routers form full adjacencies with the DR and BDR. Routers remain two-way with each other. That's expected behavior, not a problem. Next up, we'll talk about OSPF router types, basic configuration, and how everything we've learned so far actually gets turned on. Now, it's important not to confuse DR and BDR with OSPF router types. DR and BDR are segment-level roles. OSPF router types describe a router's position in the overall topology. There are 4 OSPF router types that you need to know for the CCNA. An internal router has all of its interfaces in the same area. A backbone router has at least one interface in Area 0. An area border router, or ABR, connects multiple areas, and one of those areas must be in Area 0. And finally, an autonomous system boundary router, or ASBR, which injects routes from another routing protocol or static routes into OSPF. Remember this distinction. DR, BDR are how routers behave on a shared network. ABR, ASBR, how routers fit into the OSPF hierarchy. Cisco loves testing that difference. Now, let's actually turn OSPF on. To enable OSPF, you start with, at global config, router OSPF 1. The number here is the process ID, and this is important. The OSPF process ID is locally significant. It does not need to match between routers. Next comes the network command. Network 10.0.0.0, 0.0.255.255, area 0. This command does 3 things. It matches interfaces using the wildcard mask. It enables OSPF on those interfaces. It advertises the connected network into OSPF. It does not create routes by itself. It selects interfaces. In small networks, a single OSPF area is fine, but in larger networks, a single area creates problems. Large databases, more CPU usage, slower convergence. Multi-area OSPF solves this by dividing the network into smaller areas. OSPF uses a hierarchical design. At the center is Area 0, called the backbone area. All other areas must connect to Area 0, either directly or through an area border router. Routers inside an area know the full topology of their own area, but only summary information about other areas. This is where ABRs come in. An area border router has interfaces in multiple areas, maintains separate LSDB for each area, controls what routing information moves between areas. On the CCNA, remember this. Routes within the same area appear as a O. Routes learned from another area appear as OIA. Hopefully, at this point, you understand how OSPF is designed, how it communicates, and how it's configured. If you're still a little shaky up to this point, pause, go get some coffee, and replay the last 10 minutes or so. Before we configure multi-area OSPF, let's reset the big idea. Multi-area OSPF exists to scale large networks. Instead of every router knowing everything, OSPF divides the network into areas. Each area has its own link state database, and it limits how much topology information routers must process. At the center of it all is Area 0, the backbone. Area 0 is not optional. It is the backbone area, and all inter-area traffic must pass through it. Here are the rules you must remember for the CCNA. All non-backbone areas must connect to Area 0. Routers in different areas do not form adjacencies. Area boundaries are enforced by area border routers. If Area 0 is broken, multi-area OSPF breaks with it. An area border router, or ABR, is a router that has at least one interface in Area 0, has at least one interface in a non-backbone area. ABRs are special because they maintain a separate LSDB for each area. Control which routing information moves between areas. Advertise summary information, not full topology. This is what keeps OSPF scalable. Multi-area OSPF changes how routes appear in the routing table. Routes learned inside the same area appear as O, intra-area routes. Routes learned from another area appear as OIA, inter-area routes. This is one of the clearest indicators that multi-area OSPF is working correctly. Configuring multi-area OSPF is straightforward once the design is clear. You simply place different interfaces into different areas. Remember, you're not enabling subnets, you're enabling interfaces that are in those subnets. So for example, your ABR configuration would be at global config, router OSPF 1, network 10.0.0.0, wildcard mask 0.0.0.3, area 0. And if you wanted to configure another area, same global config, router OSPF 1, network 10.1.0.0, wildcard mask 0.0.0.255, area 1. In this example, the first network places an interface into area 0. The second network places an interface into area 1. That router automatically becomes an ABR. No special command is required. Let's summarize what multi-area OSPF actually changes. Routers only know full topology for their own area. ABRs connect areas together. Routes between areas are summarized. SPF calculations are limited to each area. And most importantly, multi-area OSPF improves scalability without changing how OSPF fundamentally works. Now, before we touch on verification, we need to understand how OSPF actually chooses a path. OSPF does not use hop count like RIP. It uses a metric called cost. Cost represents the relative speed of a link. Lower cost means a better, more preferred path. When OSPF calculates a route, it adds up the outgoing interface costs along the path, and the path with the lowest total cost wins. By default, OSPF calculates cost using this formula. Cost equals reference bandwidth divided by interface bandwidth. The default reference bandwidth is 100 megabits per second. This creates an important limitation. Any interface that's 100 megabits or faster ends up with a cost of 1. So fast Ethernet, gigabit Ethernet, and even 10 gig links all look the same to OSPF, unless you change something. There are two ways to influence OSPF cost. The first is by changing the interface bandwidth, but that affects other features too, so it's usually not ideal. The preferred method is to manually set the OSPF cost. At global config, interface gigabit Ethernet 0/0, IP OSPF cost 50. This command directly sets the OSPF cost for that interface and overrides the bandwidth-based calculation. Lower cost wins, always. In modern networks, the default reference bandwidth of 100 megabits isn't enough. To accurately compare faster links, you can adjust the reference bandwidth. From Global Config, router OSPF 1. Auto cost, reference bandwidth, 100,000. This sets the reference bandwidth to 100 gigabits. Here's an important CCNA rule. The reference bandwidth must be the same on all OSPF routers, or path selection becomes inconsistent. Now, let's talk about MTU, Maximum Transmission Unit, because MTU issues can break OSPF in confusing ways. MTU defines the largest packet size that can be sent on an interface without fragmentation. OSPF checks MTU during adjacency formation. If two routers disagree on MTU, they may see each other as neighbors, but fail to reach full adjacency. This often shows up as neighbors stuck in EXSTART or Exchange. Here's the key distinction. Layer 2 MTU affects OSPF adjacency. Layer 3 IP MTU affects packet forwarding. If OSPF won't go full, check Layer 2 MTU first. You can set Layer 2 MTU by going to Global Config, entering your interface G0/0, and follow it by MTU 1500. If you're looking for Layer 3 packet size, same process, but IP MTU 1500. For OSPF adjacency issues, mismatched Layer 2 MTU is the usual culprit. A passive interface is an interface that advertises its network into OSPF, but does not send hello packets and does not form adjacency. This is commonly used on LAN interfaces where no other router exists and also increases security. From Global Config, router OSPF 1, followed by passive interface Gigabit Ethernet 0/1. Passive interfaces improve security and reduce unnecessary OSPF traffic. Loopback interfaces are logical interfaces that never go down unless manually shut. In OSPF, loopbacks are important for two reasons. They provide a stable router ID, and they also advertise stable networks. That's why OSPF prefers loopback addresses when choosing a router ID. From Global Config, interface, loopback, and the number you want it to set, followed by IP address 192.168.0.1, 255.255.255.255, because best practice is a /32. Sometimes routers need a path to unknown networks. That's where default routes come in. To inject a default route into OSPF, the router must already have a default route. To set a default route, you gotta go to Global Config, and then the command is IP route 10.0.1.0, 255.255.255.0, and its next hop address, 10.0.3.2. Once you have your default route set, you can then use from Global Config, router OSPF 1, default information originate. That route then is advertised into OSPF. However, when injected, the default route appears as an external OSPF route in the routing table. Now that we've finally covered every configuration lever, cost, MTU, areas, and interfaces, we're finally ready to verify and troubleshoot OSPF properly. At this point, we've covered OSPF concepts, configuration, cost, MTU, and multi-area design. If you're still unsure, retry the video or go back 10 minutes just to pick up where you left off. Now it's time for verification. OSPF verification commands aren't just about checking boxes. They answer specific questions. When something breaks, Cisco expects you to think in this order. Do I have neighbors? Are adjacencies formed? Is OSPF running on the correct interfaces? Did routes actually get installed? Each of the verification commands answers one of those questions. From the enable prompt, show IP OSPF neighbor. This is the first command you run when troubleshooting OSPF. It shows your neighbor router IDs, neighbor state, DR and BDR roles, dead timer countdown, and the interface used. How to interpret it? Full means adjacency is complete. Two-way is normal on Ethernet for non-DR routers. INIT or EXSTART usually means a configuration or MTU problem. If you don't see neighbors here, nothing else matters yet. Show IP OSPF interface brief. This command shows which interfaces are running OSPF, the area each interface belongs to, interface cost, DR, BDR, and DR other role, neighbor count per interface. This answers questions like, is OSPF enabled on the right interface? Is this interface in the correct area? Is DR, BDR behaving as expected? If an interface isn't listed here, OSPF is not running on it. For deeper OSPF troubleshooting, use Show IP OSPF interface. This command shows hello and dead timers, network type, OSPF interface cost, DR and BDR information, neighbor and adjacency state, and this is the command you use when neighbors won't reach full. Timers might be mismatched. You need to verify DR or BDR elections. If hello or dead timers don't match, adjacency will never form. Show IP OSPF database displays the link state database. This shows LSAs known to the router and network topology information, per area LSDB contents. At the CCNA level, you don't need to decode every LSA. What you do need to understand is this. If routers are fully adjacent, their LSDBs must match within the same area. Missing LSAs usually mean adjacency or flooding problems. Show IP route OSPF filters the routing table to show only OSPF routes. This is how you confirm routes were actually installed. Route types are correct. Here are some key things to recognize. O is intra-area route. OIA is inter-area route. OE1 or OE2 are external routes. If routes aren't here, OSPF didn't select them, even if neighbors exist. Show IP protocols gives you a summary view of routing protocols. It shows OSPF process ID, router ID, areas, advertised networks, and administrative distance. This command answers, is OSPF running? What router ID is being used? Are the correct networks included? It's a great sanity check before deeper troubleshooting. Here's the CCNA troubleshooting mindset you should memorize. Check neighbors, check interface OSPF status, check timers and MTU, check the LSDB, check the routing table. Cisco questions often test this logic, not just commands. Alright, we're here at the end. Let's do one final wrap-up. OSPF is a link state IGP designed for scalable networks. Hello packets create neighbors. Adjacencies exchange routing information. LSAs build a shared LSDB. SPF calculates best paths. Areas improve scalability. Cost determines path selection. Verification proves everything worked. If you understand why each step exists, OSPF stops being confusing and starts being logical. If this walkthrough helped you understand OSPF just a little bit better for the CCNA, hit like and don't forget to subscribe. It really helps out. But for now, what CCNA topic would you like covered next? Spanning tree? DHCP? The OSI model? Let me know in the comments below. Thanks for watching, and I'll see you in the next one.